You know, we think of them as the universe's ultimate monsters, right? These cosmic vacuum cleaners, gateways to, well, to oblivion. But is that really what they are? We're going to dive right in, because what's truly hiding inside a black hole, it might just flip our understanding of reality completely on its head.
So what really happens if you fall into one? I mean, what would you see? Is it just a one-way ticket to nothing? Or is it something way, way stranger? This is, without a doubt, one of the biggest puzzles in all of physics. And today, we're going to take a trip together, right to the edge of what we know, to try and find some answers.
All right, so before we take the plunge, we've got to get our bearings. Let's talk about what we're really up against here, what a black hole actually is, and maybe more importantly, what it isn't.
Okay, first things first, let's bust a myth. When you hear black hole, you might picture, well, an empty hole in space. But it's actually the complete opposite. A black hole isn't empty at all. Just try to imagine something with the mass of a giant star, I mean way bigger than our sun, crushed down into an area smaller than a single city. It's that unbelievable density that creates a gravitational pull so strong, it's like a prison that not even light itself can escape.
And you know, this whole idea isn't just something out of a sci-fi movie. It's been cooking for centuries. Seriously. The first hints go all the way back to the 1700s with this concept of dark stars. Then along comes Einstein in 1915, and his theory of general relativity gives the idea some real mathematical teeth. And it wasn't until 1967 that the physicist John Wheeler gave it that super catchy name we all know, the black hole. So yeah, it's been a long road to get here.
All right, you've decided to go for it. You're taking the plunge. First thing you're going to come across is the most famous part of a black hole. And it's a place from which there is absolutely no return. We're talking about the event horizon. Now, this isn't some physical wall you'd bump into. Think of it more like an invisible line drawn in space-time. But the moment you cross it, that's it. You've gone through a one-way door. From that point on, every direction you could possibly move, it all leads to one place, the center. There's no turning back, no escape.
And this is where things get really, really strange, thanks to relativity. For anyone watching you from a safe distance, say your friends back on the spaceship, it would look like you were slowing down. You'd get redder and redder and then just freeze, stuck at the edge for what looks like forever before fading away. But for you, the person actually falling in, you'd just sail right across that line without noticing a thing. At first, anyway. You'd have no idea you just passed the point of no return.
Now, I say sail across, but that might be a little too gentle. It really depends on the black hole. If it's a smaller one, a stellar mass black hole, the tidal forces would be insane. The pull of gravity on your feet would be so much stronger than on your head that you'd get stretched out like a piece of spaghetti. And yeah, that's actually the technical term, spaghettification. But if you picked a supermassive black hole, the kind at the center of galaxies, the gravity at the edge is much gentler. You might actually cross the event horizon totally intact.
Okay, so let's imagine you made it across in one piece. You're inside. Now what? Well, from this point on, the universe you used to know is gone. The rulebook has been thrown out the window.
Because inside the event horizon, space and time do something incredible. They basically swap roles. Think about it. Out here, in our normal lives, we're all constantly moving forward in time. But we can move wherever we want in space, right? Back, forward, left, right. Inside a black hole, that flips. You are now forced to move toward the center in space, just as inescapably as you are forced to move into the future. You can't stop, you can't turn around. And all of this is happening in complete and utter darkness, since no light can get in to show you the way.
Just let that sink in for a second. Moving forward in time is moving deeper into space. It means the singularity, that central point, isn't a place in space anymore. It's a moment in time. It's your future. It's an appointment that's now in your calendar, just like next Monday morning. And there is absolutely no way to cancel it.
So what exactly is this appointment you're heading to? Well, according to Einstein's classical view, it's the singularity. This is a point of zero volume and infinite density. All that mass from the original star crushed down to nothing. It's the place where our understanding of physics, of space-time itself, just breaks. It's supposed to be the end of the road. But is it really? Because that idea that the end of the road is just nothing, that creates a huge, huge problem.
We're talking about a paradox so big that it pits the two great pillars of modern physics against each other, in a real clash of the titans.
Okay, to get what this problem is all about, let's use an analogy. Imagine you burn a book. Now, the book is gone, sure, but all the information that made it a book, the story, the words, the cover art, it isn't truly destroyed. In theory, you could piece it all back together from the smoke, the ash, the heat. The information is just scrambled. But what happens if you toss that same book into a black hole? Where does that information go? Does it just poof, vanish from the universe forever?
And that right there is the heart of the paradox. On one hand, you have quantum mechanics, our rulebook for how everything on a tiny scale works, and it has a fundamental law. Information can never be destroyed. It can change form, but it can't just disappear. But on the other hand, you have black holes, which seem to be the universe's ultimate information shredders. They appear to take information and delete it permanently. So something's got to give. One of these cornerstone theories has to be incomplete.
But wait, there are a couple of major twists in the plot. First, Stephen Hawking figured out that black holes aren't completely black. They actually leak a tiny bit of energy, what we call Hawking radiation, and over incredible amounts of time, they evaporate. Which brings up the question, if the black hole disappears, where did all the information inside it go? And then there's this wild idea called the holographic principle. It suggests that maybe the information never really made it inside at all. Maybe it's all perfectly preserved, encoded on the 2D surface of the event horizon, like a cosmic hologram. These are big clues that something else is going on under the hood.
And that's something deeper? That's what brings us right to the absolute cutting edge of physics today. Because brand new research is starting to challenge that 100-year-old picture of what's really at the heart of a black hole.
Which leads us to the big question, the one this new research is tackling head-on. Is the singularity, that point of infinite density where physics breaks, is it even real?
Well, an absolutely groundbreaking study from February 2025 says, maybe not. For the very first time, a team of physicists led by Enrico Rinaldi was able to use quantum computing to actually simulate the core of a black hole. They modeled what it would look like not as a collapsing point, but as a stable quantum system. This is something we have never, ever been able to do before.
And what they found could completely redraw our map of a black hole. Instead of the old classical view, this infinitely dense singularity where physics just dies, the new quantum model suggests the center is a really complex, highly structured quantum state. So the laws of physics don't break, they just become different, new laws that we're just starting to understand. And here's the kicker. This means information isn't destroyed. It's encoded and preserved right there in that quantum structure.
You see, this is way bigger than just understanding black holes. This could be the breakthrough we've been looking for. It's a potential bridge between Einstein's world of gravity and the weird world of quantum mechanics. Finding a quantum system that acts like gravity, that's a massive step toward what physicists call the Holy Grail, a unified theory of quantum gravity, a theory that could explain pretty much everything.
And that's really what this is all about, isn't it? This isn't just an academic puzzle. This breakthrough is about understanding the universe itself. These extreme objects, these black holes, they are the ultimate laboratories for testing our most fundamental ideas about reality. And if we can crack the code of a black hole, well, we might just be able to crack the code of the entire cosmos.
So I want to leave you with one final kind of mind-blowing thought. If that holographic principle is right, if everything that falls into a 3D black hole can be described by information on its 2D surface, then what about us? What about our universe? Could it be that our entire 3D reality is just a holographic projection? Information written on some vast, distant, two-dimensional cosmic boundary? So what's really inside a black hole? Well, the answer might just be everything.